Hi everyone, my name is Chen Hao and today I'll be motivating the Fenwick tree from buckets. So the Fenwick tree is a data structure that allows for O log n point updates and range sum queries, and is also known as the binary index tree, and was invented in 1994 by Peter Fenwick, and this is a picture from the original paper. So here's an overview of how the Fenwick tree works. I won't go into great detail, there are other videos on YouTube for that. So the Fenwick tree is an array, just that each index does not represent the element at the index. Instead, each index of the Fenwick tree array represents a sum of some range. So how I can obtain this range is by looking at the index minus the least significant bit of the index. So for example, 8 over here, index 8 of the Fenwick tree represents the sum from ranges 1 to 8. And let's say index 6 over here represents the sum from index 5 to 6. So if I want to do range sum queries, it's equivalent to performing prefix sum queries because I can just take the difference. So if, for example, I want to query the prefix sum from index 1 to 7, it decomposes as 1 to 4 plus 5 to 6 plus 7 alone. And the reason why I decompose it this way is because the Fenwick tree has stored the sum from 1 to 4 at index 4 of the Fenwick tree, and index 5 to 6 at index 6 of the Fenwick tree, and 7 is just 7 alone. So another example will be index 10, right? Index 10 decomposes as 1 to 8 plus 9 to 10. And these ranges are conveniently stored as a single value in the Fenwick tree. So instead of summing up 10 elements, right, I can just sum up 2 elements in the Fenwick tree array. And in the worst case scenario, I sum up to log n elements, because if every bit in the index bit binary representation is 1, for example 15 is 1111, then it'll sum from 1 to 8, 9 to 12, 13 to 14, and 15 alone. So that's the worst case scenario. And O log n is a huge time saving from O of n, which is the naive method. So that's for range sum queries. But what about for point updates? We want to update the elements in our Fenwick tree as well. So for point net updates, we look at for each element we want to update, we look at what ranges it affects. For example, if you want to update index 6, right, we draw a vertical line up and we look at this diagram and we look at what ranges contains this 6. What ranges does this line intersect? In this case, it intersects 2 ranges from 5 to 6 and from 1 to 8. We can compute this by using the least significant bit as well. Actually, we just add it. Yeah, so in the worst case scenario, an update also costs log n ranges to be updated. For example, if we update index 1 over here, it hits all these 4 ranges. So for a long time, when I did competitive programming, I treated the Fenwick like a black box. And recently that changed because I was watching this lecture on VEB trees and I got inspired by the bit trick that he presents. By the way, this lecture series by Professor Domain is awesome. It's totally awesome. So do check it out by yourself, and I'm sure you'll learn a lot of things from there. So I realized that we can use bit tricks to motivate Fenwick tree from buckets. And today that's what I hope to cover. So basically, here's a summary of what I'm going to talk about next. So Fenwick tree is multi-layer buckets plus some amount of space saving, right, using an observation, and also making use of binary indexing. So here's I'm going to slowly get to buckets, but first let's talk about the naive method. So if I want to perform point update and prefix sum queries, one way is just to have a naive array, right? Just have every element being one element in the array. Then the time complexity for prefix sum will be O of n. So for updates, right, we're just updating a single element. We're just changing the element in the array. That's O1. And for range sums, right, it'll be you can take it as you can just have a for loop that goes through every element in the array and sum it up. But the worst case time complexity is On for a size n array, which is not good. So we can actually save a lot of time by adding buckets. So the observation here is that we don't want to recalculate too many sums, right? We don't want to calculate the sum of many elements too many times. So we create a kind of a mini summary of sorts. So for 16 elements over here, I chose a bucket size of 4. That's the optimal bucket size. And every 4 elements, I sum it up and and store it in somewhere, right? Store it in a bucket, in another array. And so now every point update, let's say I update this 8 to a 9 over here, right? Every point update, it costs only one time, because I just look at the amount that I added, right, to this array element, and I go up to the bucket that stored is sum, and I update it as well, adding 1, right, adding the amount that I added to the array element. And so now every point update just takes 2 operations, right? One for the array itself and one for the bucket that it belongs to. And now prefix sums can be performed in O square root n as well, because you see, if we want to query the prefix sum up to this element 5, instead of summing up 1 plus 6 plus 9 plus 3, right, plus 4 plus 1 plus 9 plus 9, and so on until this element 5, I can just realize that I've computed a sum from 1 to 3, right? These 4 elements, I've computed the sum and stored it in a bucket somewhere. And so I can just retrieve that sum and not recompute the sum again. And likewise for 4199. And so we can just use these 2 bucket values instead of performing the sum of each array element. However, right, we realize that because the querying point over here, the querying index, it cuts into this 17 bucket, right? It does not include 8. So unfortunately, for that bucket, we have to manually sum up the elements. However, because we chose the bucket size to be square root n, the number of elements we have to sum up in the bucket manually, right, doesn't exceed square root n, right? So the time complexity for prefix sums as a whole becomes square root n instead of on. So the idea is that instead of we do some amount of pre-computation that is quite easy to update if we change the array, and now if we want the prefix sum, we can use some of the pre-computed values, and instead of recomputing that entire sum, and because each bucket size is square root n, right, there's at most square root n buckets, because n divided by square root n is square root n. So because I've chosen the bucket size to be clever, right, the number of buckets I have is also square root n. So no matter what prefix I want to, no matter what range I want to query the sum of, the number of buckets and the number of elements in each bucket doesn't exceed square root n. So the total time complexity is O square root n. So that way we save some time. And if we, let's say we bring another example, right? If I want to sum up all the way up in the index 9, right? Instead of summing up 3, 1, 5, 8, right? We realize that was already computed, so we just take the bucket's value. And 9, it doesn't fulfill the entire bucket, right? It's a lone element, so we have to sum it individually. So buckets is a great idea. So why not we just add another layer of buckets and try to save even more time? And it turns out that's exactly what we can do, right? We can do this. If we add another layer, we actually get cube root of n, and the number of layers is the nth root, right? So for example, if I have 10 layers, then there'll be 10th root of n. And it turns out if we bring this idea to the extreme, then we actually get a Fenwick tree. But when we get there, so if for example I have 27 elements, I chose 27 because it has a nice cube root, then the bucket size will be cube root of n, and that means that for every 3 elements, right, 3 being the cube root of 27, for every 3 elements in the array, I form 1 bucket. And for every 3 buckets at the second layer, right, I form another bigger bucket, the red bucket. So now I have 3 layers of buckets, right? So at the top layer, I have buckets of size 9, right? At the second layer, I have buckets of size 3, and at the third layer, I have each individual element, right? So yeah, so if we bring this idea even further, right, we see that the bucket size previously was square root n. Then when we add another layer, it becomes cube root n. If we add another layer, it'll be 4th root of n, and so on. And we bring to the extreme, the bucket size becomes 2. And at that point, it doesn't make sense to decrease it further, because if we're going to store less than 2 elements, right, if we're going to store 1 element in the bucket, then that's just the array element itself. So log n is the furthest number of buckets you can go. So if we observe the trend over here, for 2 layers of buckets, right, the time complexity for point updates is 2, because there's 2 things to update. There's 2 layers to update, right? For 3 layers, the time complexity for point update is 3. So for log n layers, right, which gives us a bucket size of 2, the point update time complexity is log n. And likewise, if we take a look at prefix sum, it went from square root, cube root, and so on until if we have log n layers, then it'll be log n for the prefix sum. So here's a graphical representation of what that looks like, right? Every 2 elements, I form a bucket. Every 2 buckets, I form a bigger bucket. Every 2 bigger buckets, I form an even bigger bucket. Every 2 even bigger buckets, I form the biggest bucket until I get to 1. So here's an overview of what that looks like, right? The time complexity for updates is equals to the number of layers there are, because each update, right, each update over here, we need to traverse all the buckets that it affects. And in this case, it's log. It's the number of layers, right? So the update time complexity is the number of layers. And the sum time complexity is actually n to the power of 1 over the number of layers. So for log n layers, right? So I chose n equals to 64 elements in this example because it is a nice square root. It has a nice square root, it has a nice cube root, and it has a nice logarithm. So yeah, so for log n layers, the time complexity for update is log n because it's just following number of layers, and the sum is what n to the power of 1 over log n, which is actually just log n itself. Yeah. So okay, so that's the buckets idea, right? We see that basically this is we're almost there, right? This is almost a Fenwick tree, but we see that it's not quite the same, right? In fact, we have taken up, it seems like we need a lot more space, right? In fact, if we look at buckets itself, we actually need to create more space, but we'll get to how we can save space and actually just use the original array itself. So in this case, it may seem like we need n space complexity of on, right, plus n over 2 plus n over 4 plus n over 8 plus n over 16, which it totals up to n log n. But that's actually not the case, because we can make the observation that actually the last element of each bucket is, we don't need to store it. So for example, if we have just 2 layers of buckets over here, to keep it simple, we realize that this tree is actually redundant. We never need to use the tree, because if we perform prefix sum queries, right, if we perform prefix sum queries, we're always going to ask for, we may ask for 1 alone, we may ask for 1 plus 6, we may ask for 1 plus 6 plus 9, but the moment we ask for 1 plus 6 plus 9 plus 3, right, the moment we invoke that tree, we realize that actually, hey, we have already stored the entire sum in this bucket. So actually this tree is redundant. Likewise, this 9, right, for each bucket's last element, we actually do not need to store it, because if we want to query the prefix sum of the entire bucket, then if we want to query all the way to the last element, then we can just use the bucket's value, the pre-computed value instead. So that's why, right, we remove the last element of each bucket, and we see that nicely, right, that creates square root of n slots, right, because each bucket has 1 last element. So now that this 19, right, we don't need to create a new array for it, we can just put it over there. So likewise, if we extend this idea to the log n layer buckets, right, the first layer, the last layer, we can remove these elements. The next layer, these 12, 17 can also be removed. The next layer can also be, the last element can also be removed. And the next layer, last element can also be removed. And this is actually the Fenwick tree. So basically, we have covered 2 parts of the Fenwick tree now, right? Fenwick tree was multi-layered buckets plus saving space, right? And the last part of it is the binary index part. So this is the key idea of the Fenwick tree, but how do we do it how do we implement it? So yeah, so how do we, where does the binary index tree come from? So it's actually using the binary representation of the index to calculate what ranges it sums to. So let's go back to the buckets example, right? This is where the Venom debose, right, the VEB trees comes in, and this is the inspiration for how I came up, how I wanted to, this is the inspiration for this video. So if we look at n equals to 64, right, we represent it by 6 bits, right? So 0 to 63, right, it can be represented by 6 bits of information. So for example, if I have the number 13, I represent in binary. If we take a look at the binary representation and we cut it halfway, right? So 6 bits, we cut it halfway, 3, 3. Then the first 3 bits actually represents the floor of that number's divided by square root n. And the last 3 bits actually represent the number modulo square root n. So what is this useful for, right? This is the observation so far, but we can actually apply it to the buckets. So okay, another example, I reduce 64 to 16 because I'm going to show you a diagram next. So if we have n equals 16, x equals 9, right? We see that same computation applies, just that instead of having 6 bits, we have 2 bits. We have 4 bits. So it splits into 2, 2. So the first 2 bits actually represent the index of the bucket. So in this case, you see 9, element 9 over here in green, right? It belongs to the index 2 bucket, right? Where is 0 index. And the second 2 bits, right? The second 2 bits 0, 1 actually represents the element in the bucket. So basically, the binary representation of a number, right? When we split it in half, in terms of the number of digits, the first half represents the bucket that it belongs to, and the second half represents the position in the bucket that it belongs to. So if we now take a step further, bring up the cube root, right? We split. I need to go back to n equals to 64 again because that has a nice cube root, whereas 16 doesn't. So if we look at the 6 bits that it has, we split into 3 segments, right? The first third, second third, and the third third. So these 3 segments of 2 bits, right? These 3 sections of 2 bits represents the different layers. So if we bring this idea even further, we get the Fenwick tree. So yeah, for example, in this case, index 9 over here, if we look at the Fenwick tree, right, the binary representation is 1001. And yeah, actually, so that's essentially how we get that's why we name the Fenwick tree the binary index tree. And there's one more question over here, which is so this is a bit of extra part, but why is it 0 indexed when I mentioned first that there's 1 index? It's actually due to ease of implementation. So for example, one can make the observation that when we want to traverse up the Fenwick tree, we actually perform this computation where we calculate the number of ones before the first 0 in the binary representation of the index. But this is inconvenient code to implement, and instead it's actually, if we just add 1 to the indices, right, we can actually make use of this 2's complement trick to get the least significant bit of some number. And another extra fact is that previously we saw this, right, before we save space, this is actually a segment tree, which roughly speaking is 2 copies of a Fenwick tree. So a Fenwick tree is nice because it allows you to do prefix sums, but it is not nice because for elements that you cannot convert a prefix query to a range query by taking the negation, right, for basically for mathematical operations that do not have an inverse, such as minimum or maximum, for such mathematical operations, you cannot build a Fenwick tree for it, because it doesn't have an inverse. So you cannot turn the prefix into a range query. Yeah. So instead, you actually need to have a suffix. You actually need to have a suffix of sorts. So you have one copy for handling the prefixes and one copy for handling the suffixes, and that is actually 2 copies of a Fenwick tree. Which, if you take this diagram over here and you turn and you flip it, you mirror it, right, you mirror it over, then you piece it together, you basically get the segment tree, and that also has log n for time complexities, but the implementation is a bit more involved. So anyway, I hope that I've successfully motivated the Fenwick tree from buckets, and if you did like it, please leave a like and leave a comment about any ideas that you have. Thank you.